Hello. All right. Here we go. Chapter 3. So a lot of this should be fairly familiar with you, but I'll go through it fairly quickly here. 3.1 is about functions. Okay. And let's see. So they talk a little bit about this credit card function. You should read this. It's kind of interesting. It's a way to verify whether a particular credit card is valid or not by they take the numbers of the credit card, they double them, add them together, you get some number, and then if you so it says here if the last digit of the sum is zero, then this thing called the check digit is zero. Otherwise, you subtract the last digit from of the sum from 10. In other words, you get 7, and that's how you can determine whether or not these original numbers come from a credit card. So, yeah, you can read through that. It's kind of interesting. It's an actual application there. So, all right, then here's a little definition of a function from a set x to a set y. And you should be familiar with that. Make sure that you are. Here's an example. Let's see. I'll go through this. So this set, one here, f is written this way. Basically means f of 1 is a, f of 2 is b, and f of 3 is a, as is illustrated by this picture, right? So that's a function. Let's see what this is. So it says this set here, it says is not a function. So let's take a look at it. 1, 2, 3, a, b. Okay, so we do get a unique answer, but what's the problem? So the problem is that the domain is too large, right? So, yeah, that's why it's not a function. We would need to define what the value of the function was at 4 for it to be a function. Okay, continuing on, let's see. Here's just some notation, right? I'm sure you're familiar with this notation. And okay, so if we call the check digit function L, we may write. So that was when, remember when we doubled everything up there for the credit cards, we get 7. So this is just different notations for functions. Normally, you can think of it this way. What is this? This must be the graph of a function. Is that what we're talking about here? Yeah, if you look at the set of all ordered pairs, right, x squared, where x is a real number, right? What are we talking about? Okay, they're just talking about domain, codomain. Okay, so the range, I'm sure you've seen all this before. So let's get down here. I want to go through a couple of examples. Here's a nice example. We're going to be using this modular function quite a bit. So here's a definition of it. If x is an integer and y is a positive integer, right, we define x mod y to be the remainder when x is divided by y. Okay, so for example, 6 mod 2 is 0, since 6 divided by 2 is 3 with a remainder of 0. Let's see, 5 mod 1 is 0, since 5 divided by 1 is 5, the remainder of 0. Let's see, 8 mod 12 is 8, since, 8 divided by 12 is 0 plus 8. And you can check this out. This number, mod 2, is equal to 1. And the reason for that is fairly clear. That's an odd number. So you're going to be, when you take that 199,673 divided by 2 is equal to something plus 1. And that's where that 1 comes from. Oh, here's another interesting. So the check digit that we talked about up there with the credit cards could be written this way. So you take 10 minus the sum mod 10, and you can check to see that that in fact works. Yeah, so, right. Okay, okay, here's an interesting little example. What day of the week will it be 365 days from Wednesday? Well, okay, so what do we do? So Wednesday, we know every 7th day it comes back around to Wednesday. So essentially what we're doing is we want to calculate 365 mod 7, right? and what that's equal to a 1. So 1, right? It's not a 0. So if it were 0, then for example, 364 days from now would be a Wednesday, right? So yeah, so 365 days from Wednesday, it'll be 1 day later, or Thursday, right? That's what that 1 tells us. So this modular function will be quite important for us. Here's an interesting little concept. This idea of the pseudo random numbers. So it's quite important to try to be able to generate random numbers in our world to try to simulate this idea of randomness. And one way to do it is by using our modular function here. So what you do is you say, you have this function here, and you pick, so what they do is they pick a seed S, right, satisfying 2 is less than or equal to A, less than, so that's the multiplier, right? Then you take some number C, which is less than M, so that, and then you pick S, where is our starting point. And then what you do is you just continuously calculate this over and over. For example, whatever number you pick in there will be some number between 0 and M, right? And then you plug that in again, and it generates an entire sequence. So for example, if M is 11 and A is 7 and C is 5 and S is 3, then X1 would be calculated as 4, and then you plug 4 in to get for X2, right? And if you find X2, so you get 0. And if you keep doing that, notice what happens is you get, here's your numbers, your pseudo-random numbers. 5, 7, 10, 9, 2, 8, 6, 3, right? And then, okay, so you got a 3 here, right? And here what they're saying, that's the seed value. So the one of the, I guess the problems with this method is that it generates a finite repeating sequence, right? And that repeating sequence will have length at most M. So you need to pick large M's, and that's what they're going on here. If you pick huge M's, then it's very difficult to detect the sequence that's being generated. So, okay, another really important function that we'll be using over and over and over again are the floor and the ceiling of a real number. So I think we've seen this once before in this class, but the floor of X is denoted with an X and then a little, see those little bottom things on the bottom. That's the greatest integer less than or equal to X. And the ceiling of X denoted looks very similar, except there's little bars above it. That's the least integer greater than or equal to X. So here's the graph of those functions, right? So those are very important functions in when you're using computers and discrete mathematics, because it takes the real numbers and it turns it into a discrete set. Okay, let's see what we have here. Here's just an example of how you would calculate that. So if we had this function P, right, I guess is the postage function, right? Okay, the first class postage rate for mailing up to 13 ounces is 92 cents. And then for 1 ounce or fraction thereafter, and 20 cents for each additional ounce and or function fraction thereafter. So you do this, you say, okay, so we would the price of postage would be 92 cents plus, and then you take 20 times, and then you use this ceiling function, right? And where W, I guess, is the that would be what the number of ounces over, and yeah, that gives you the I mean that'll give you the what the deal is, right? So it's a way of getting this function written down nicely. Let's see, here's okay, and then obviously we're going to very much so need to know the concept of one-to-one function. So a one-to-one function is the same as you've heard many times in your educational career, that if you're given two numbers, x1 and x2, then if f of x1 equals f of x2, it only happens when x1 is equal to x2. Okay, so we will need to use that little example here of if x is a set of people who have social security numbers, and we assign each person x and x has his or her social security number, SS of x, we obtain a one-to-one function since distinct people are always assigned distinct social security numbers. Okay, little example there. All right, let's say here's a little exercise. We can see how we can use these definitions. Let's prove the function f of n equals 2n plus 1 from the set of positive integers to the set of positive integers is one-to-one. Well, okay, what you do, you pick two numbers, n1 and n2, and you evaluate them, and then let's see what we get. Oh, so we see that we get 2n1 plus 1 equals 2n2 plus 1. If you solve this equation, you can conclude that n1 equals n2, and that's how you, as you have in the past, show that a function is one-to-one. Okay, let's prove that this function is not one-to-one. Okay, so what does this mean? Let's see, prove that the function f of x equals 2 to the n minus n squared from the set of positive integers to the set of integers is not one-to-one. Okay, so what does this mean? So it means exactly what they're saying it means. we have to find positive integers n1 and n2, where n1 is not equal to n2 such that f of n1 equals f of n2. So they're talking about checking the graph here, or otherwise we can find that f of 2 equals f of 4. Okay, do I believe that? Well, let's see. Well, I guess so. You just plug it in there. Well, yeah, you plug in a 2 here, you get 2 squared is 4, minus 4 is 0, and yeah, so this is not a one-to-one function. Okay, the idea of a function being onto, you should be familiar with. So a function f from x to y is said to be onto y if for every y in y, there exists an x in x such that f of x is y. Okay, very familiar to what you've done before. Let's see, let's do this example here. Prove that the function f of x equals 1 over x squared from the set of non-zero real numbers to the set y of positive real numbers is onto y. So what you do, you have to just use the definition. We must show that for every y, there exists an x satisfying f of x equals y. Okay, so let's do that. If we write down this equation, let y be some random number, right? If you solve for x, right, what can we do? We can just solve for x, and you see x is equal to plus or minus 1 divided by the square root of y. And the square root of y exists because we're assuming that y is a positive number. So there's actually, this function is actually 2 to 1. In other words, you could take 1 divided by the square root of y, or x equals 1 minus 1 over the square root of y, and both will give you solutions, or the number y back. Okay, so here's a definition. A function that is both one-to-one and onto is called a bijection. Those are very important, bijections, because that's how, in fact, in this example, we can prove that two sets have the same size, right? So if f is a bijection from a finite set to a finite set y, then the size of x is the same as the size of y. Okay, and that's the definition. Let's see here. Oh, then there's this idea of the inverse, right? So a function has its inverse. So if we have, here's our example. Well, yeah. Well, if a function is a bijection, right? Here we go. This is what I wanted to get to. Suppose that f is one-to-one onto function from x to y, right? So we have a one-to-one and onto function. Well, it can be shown, see example, that in fact, if I just change the order, right, write down this set, this is also one-to-one. onto function from y to x. In other words, you can change the range of the domain and think of it as a function going the other direction, backwards, right? So the new function is denoted by f inverse, and it's called the inverse function, okay? This is a very, very important concept. Let's just go through this one here. Here's a good example. It says here, the function f of x equals 2 to the x is one-to-one function from the set R of all real numbers onto the set R plus of all positive real numbers, okay? Derive a formula for f inverse. All right, so this is, it's kind of funny how they do this, but it's more or less a definition that is used. But here we go. Suppose that we have this, suppose that this is in f inverse. That is, let's suppose f inverse of y equals x, okay? Then it says xy is in f, right? Thus, y equals x squared. So by the definition of logarithm, right? So that's how we get the logarithm, is it is the inverse of this function. The logarithm base 2 is by definition the inverse of that function, right? So if you combine all this information together, you can see that, yeah, in fact, that's the answer. It's the logarithm base 2. Okay, then there's this idea of a composition of functions, right? We can compose functions just like we did in the past. In other words, if you have a function from x to y and a function from y to z, then you can get a function from x to z, and it's written this way. First you perform g, and then you perform f. It sort of looks like in reverse. You read backwards with functions, and then you get the composition. Okay, here's a good one. So if f of x is the logarithm base 3 of x and g of x is x to the fourth, then f composed with g of x is just the logarithm base 3 of x to the fourth. And this should all be a review for you if you've gone through a calculus class or anything like that. Here's a definition of function. Okay, so things like addition are a good example. So a function from x cross x to x is called a binary operation. And here's a good example. F of x, y equals x plus y. Binary operation. And lastly, we have a function from x to x is called a unary operation. Okay? So here's a good example. Let U be a universal set if we define f of x equals the complement of x, where x is in the power set of U, right? Then f is a unary operator on the power set of U. Okay, well, I hope that helps. Look through your assignments and things. I think you'll find this section to be mostly review. Okay, thank you. Bye.